Hello everyone, welcome to the GeoEcolologist. I am Dr. Krishnanand, and today in this session on climatology, we are going to discuss the most awaited topic, that is atmospheric stability and instability, along with major factors, major important points that is important to understand this phenomena. So if you have not watched the earlier videos on lapse rate and adiabatic lapse rate, it's a request that please watch those videos to understand this stability and instability factors or phenomena of atmosphere in a better way. So before we go ahead, please like and subscribe to our channel and don't forget to share the videos with others as well. So now let's discuss this phenomena that we say atmospheric stability and instability. So the first idea is, what is this stability and instability? A general connotation of being stable is what? Staying at a particular place, just sitting on your chair, being at your place. That is what is stable. And what is unstable? When you start moving away from your individual position, that is supposed to be unstable. So remember, when we are saying stable and unstable in terms of atmosphere, what are we talking about? So if you look into these two images simultaneously here, what are the situations here? Just see, this particular, which is sitting on the cliff, this ball, this is highly unstable because with a slight push, slight energy change in terms of, if we say atmosphere, what happens? There is this dislocation and it is highly unstable. But which is here in this valley, if you see this particular location, right? So if you see this particular zone, it is very stable. It can not go this side, it cannot go this side, is sitting here at one place. And also a third situation, if you see, this is a neutral situation in between somewhere these two. What is this neutral situation? It can either move this way or this way, but even if it moves, it will stay at this particular location itself. It's not going to go anywhere. So that is something which is a neutral situation. Similarly, if you observe these images, position A and then position B, what you see, this is fairly a stable situation. If you see, even if the boy pushes this ball, it again comes back at the same position. So this is highly a stable equilibrium position, right? But what is unstable? If you push it from this particular point, then what happens? It never comes back, right? So it is highly unstable. So this is what we say is unstable equilibrium. So these are basic concepts about stability and instability. Let's now understand this concept of stability and instability in context to the atmospheric circulation. Now for this, it is important to understand two important things. One is what we say is the vertical temperature distribution that we have learned in the forms of lapse rate and adiabatic lapse rate. Right? So lapse rate and adiabatic lapse rate tell us about how temperature fluctuates moving ahead in the atmosphere, right? So inversion of temperature also we have studied. So if you have not studied about lapse rate and adiabatic lapse rate, it's a request that you please go to the playlist. Before understanding the stability and instability, do learn lapse rate and adiabatic lapse rate concepts and details so that it will be easier for you to understand this stability of atmosphere and instability of atmosphere, as it is directly linked with these lapse rates that we see, right? The vertical temperature through elevation when there is a change in the temperature of this air parcel, or for that matter the entire atmosphere, in the troposphere specifically when we say. So that is important to understand how stability and instability are linked to this atmospheric phenomena. Now let's elaborate further more. So if we look further more, what you see, so what is a stable air here? Stable air or a parcel. Parcel is what? Remember, it's a packet. So when you order on Amazon and a packet comes, it's like a parcel. It's a fixed entity, right? So if we say stable air or a parcel of air whose vertical motion is actually inhibited. Vertical motion is inhibited means basically what? It is stable. It is not moving upward, right? It is at a particular place, right? So this is important. This is where we say it is a stable air parcel. Now, if an air parcel has tendency to actually come down and sit, this is a tendency to actually be stable, right? And it is also important for cloud development to be unstable at the same time. Why? If it is not unstable, it will not be rising, right? It will sit at the same place. So to rise is important for this cloud formation, right? If the air carrying moisture will not rise, then how will the cloud form? So instability is not like something bad for atmosphere. It is important for the cloud formation. So remember, stability and instability, when we hear, we think like good or bad. It's not like good or bad. It is basically characteristic of this atmospheric circulation in context when we see. So stability and instability are like yin-yang concept, right? They are actually complementary to each other for the entire climatological phenomena, for atmospheric phenomena to operate. So that is why it is important. So stability and instability in simple way is this tendency to actually rise up and fall down. So when you are rising up, you are unstable, you are mobile, you are moving. But when you are falling down, when you're coming down and sitting at your place, this is a tendency to be stable. That is what the basic connotation is that you should remember. Now, how do we determine this atmospheric stability? So for determination of this atmospheric stability, what do we do? So let's see this example of a ball in water here. What do you see? When this ball is here in water, what happens? When does it rise and when does it sink? Now remember the law of flotation, Archimedes principle, several other things. So if this mass is actually lighter, it will float up in the air, right? And if it is heavier, it will sink down. This is the basic concept, right? So what happens in terms of atmosphere? If you see, if this is a parcel of air, if this is an air packet, what will happen? If it is warm, if it is heated, it will rise up, it will float up. But when going up, it again cools down, it comes back to the ground, right? Because it becomes dense and it becomes heavy. So what happens? Cool air comes down, hot air rises up is the basic concept. So the air parcel, what is important here? The density. Light environment, it will rise. Heavier than environment, it will sink. So remember, when we say lighter than environment and heavier than environment, it means what? We have already talked about, it is a fixed packet. When we say fixed packet or parcel, there is environment all around it, right? So either its temperature will be same, or it will be higher, or it will be lower than environment, right? So that is what is the three different cases. If it is higher than environment, what will happen? If it is lower than environment, what will happen? If it is same to same as environment, what will happen? So this is what is all dependent upon this factor, that atmospheric stability will be there or instability will be there. So the major driving force, again, what is the major driving force behind this stability and instability? It's the temperature, right? So this is important, right? At a given pressure, how much is the temperature? So if temperature is injected in an air parcel, what will happen? The molecules will expand, right? The volume will increase. It will go up as it becomes light. So as it goes up, it will start to increase in the volume as well. So this is what the entire phenomena happens on the earth and atmosphere. So let's understand this stability and instability in details now. So experimentally, how do we determine this atmospheric stability and instability? A very common method, you must have heard through several lectures of others, many people, many scientists, many teachers have taught you the same method, that is air parcel method. Now why is this air parcel method so famous? Why everybody talks about it? The first important thing is that we need to understand a phenomena which is natural. So unless we are able to actually experimentally understand the process, we cannot actually generalize it. So this is a scientific kind of study where what we do is we take a fixed unit volume of air, right? That is a parcel whose mass is constant, right? And what is expanding? The volume is changing. Why volume is changing? Remember the gas laws? Because of the temperature changes, right? So if temperature changes, what will happen? Molecules will go away from each other, so volume will expand. If it is cooling down, molecules will come back, condense, it will become denser, it will fall down. This is the entire mechanism. But this air parcel method has some assumption. Now this is something unique that you need to understand, that this is not discussed generally when people say air parcel method. So what are the assumptions? Remember, the method applies to atmosphere at rest. So it is considered that when this parcel is at rest, it is not moving, it is just fixed here, it is sitting on the ground. That is the first assumption, right? Then small parcel of air in the sampled atmosphere is caused to rise. Now this is just a single important sample part of the atmosphere. So it is kind of a sample. Remember, in scientific studies, we take sample, we apply method to the sample, then apply that important result on the general atmosphere. So this is how this resultant is happening here also. So we take a sample air which is called air parcel, right? Now The rise of the parcel does not set its environment in motion. Now remember, the rise of this parcel does not set its environment in motion. This environment has nothing to do, it is not affected by this rise. So that's why we just take this parcel and see the impact of what happens with this temperature and volume changes on this air parcel. So lifting under these conditions is supposed to be through adiabatic process. So that is what the pressure temperature changes are important, volume changes are important, where one factor is constant, right? The characteristics that determine this stability of the atmosphere are what? The temperature lapse rate through the layer, then temperature of the parcel at initial level, and internal changes that happen. That is, internal changes happen that we study as latent heat of condensation, dry and wet conditions of adiabatic process, right, in the thermodynamics. So initial dew point of the parcel. Now remember, this parcel has initial dew point, that is important, where this saturation happens, where the cloud formation happens, where the latent heat release happens. So these are the important points to remember. So when you are writing an answer on stability and instability, don't just start mentioning air parcel and start with lapse rate and adiabatic lapse rate. Always mention these points that will make your answer look good, because you know the assumptions behind this parcel method of actually determining the atmospheric stability and instability. So what are the golden rules? Now remember, golden rule is the first one. Stable means resists vertical movement, right? A parcel lifted in this condition will be pushed back to the original level. So even if we take it to this particular height, it will again come back. Or even if it is this height, we throw it down, it will again go back to the same, because of this stability condition that we say, right? Because of the temperature changes that we observe. So in stable situation, unstable situation, it means that it has a tendency to actually rise, that is vertical movement is involved here. So that is why it is important that vertical movement tendency is triggered by what? Is triggered by heat action, by insolation action, right? That is important. But neutral is no effect on vertical movement. So that is another third case. If this air parcel has no effect of moving up or down, it is just fixed in this particular state where environmental temperature and parcel's temperature are equivalent, then this is a neutral state. So conditions for absolute stability is here. Remember, TD is what? It is dry adiabatic lapse rate, which is normally 10 degrees C. It is assumed as an average value. So this is 10 degrees C per kilometer. This is called dry adiabatic lapse rate, which is TD here. So TD, which is greater than TM. So TM is what? Moist adiabatic lapse rate, which is average as 5 degrees somewhere or 6 degrees per kilometer. So remember, this is the TM. So TD is greater, dry is greater than TM, which is further greater than TE, which is the environmental lapse rate, which is called ELR. If this is the situation where dry adiabatic lapse rate is most effective factor, which is most dominating factor, then moist and then environmental lapse rate, it means it is absolutely stable condition. There is no tendency of the air to actually go ahead. So what you observe here is this atmospheric stability. Now there is a case DALR. What is this? Dry adiabatic lapse rate. It is greater than normal lapse rate. So if you understand this situation, what is happening? Dry adiabatic lapse rate is higher and normal lapse rate or environmental lapse rate is lower. In this case, what happens? If it is not saturated air, remember it is dry air, it is not saturated. So what will happen? It does not attain dew point and it becomes colder than surrounding air at a certain height, with result it becomes heavier and descends. So remember, as we discussed, what happens here? This is roughly environmental lapse rate here is at 4 degree, right? And what is here? Dry adiabatic lapse rate is 10 degrees. So it is greater. So what do you observe here? What is happening? Remember, this particular parcel of air is 30 here, it is 20 here, it is 10 here, it is 0 here. But environmental lapse rate is lesser. So what happens? It is 30 here, at the same height it is 26, at the same height it is 22, at the same height it is 18. So what will happen? If this layer temperature is 18 and if this parcel temperature is 0, just understand what is the situation here. What will happen? This heavier air will start to descend down. This cooler air is heavier, so it will start coming back, right? It will not go further more. So it will have a tendency to come back. And that is where it is important to understand, when this tendency to come back is there, what is the situation? It is a stable situation. right? This is how the difference of this DALR, that is dry adiabatic lapse rate of this air parcel, and the environmental lapse rate or normal lapse rate situation is actually attached. So DALR is greater than normal lapse rate or environmental lapse rate, a stable situation is expected, right? Now, further, if we talk about atmospheric instability, which is where we are more concerned because this is regulating the entire climatological phenomena. That's why instability is very important. So it has two types. One is called convective instability, that is thermal, that is heat based. So convection happens, right, from low to high and again come back. So this is what convective cycle looks like. So it happens like that. Then we have a dynamic instability, which is of mechanical nature. So let's understand convective instability, that is thermal mixing of hot and cold air that we know. But dynamic instability is mechanical in nature. It is produced through horizontal movement of air. And remember, Coriolis force and pressure gradients, these are the forces that are important for this dynamic instability, right? So that is important. So dynamic lifting and mixing produces cloud, precipitation and storms, often were on a synoptic scale, on a regional greater level. That is important to understand here. So convective instability is the major part of atmospheric instability that we are talking here, that is the thermal instability. So now let's understand what is the case of this absolute instability. When does this absolute instability happen? So simple way to understand is when wet adiabatic lapse rate is smaller than dry adiabatic lapse rate, which is smaller than ELR, environmental lapse rate. It means ELR is the greatest. When environmental lapse rate, that we say as normal lapse rate, suppose its value goes very high, then what happens? Let's look at this particular situation. Now remember, this is that parcel of air, right? It is at 40 degrees C and the normal situation is also on the ground, environment is 40 degrees C. So these are both at the same temperature. Now it is important to understand what is the role of this environmental lapse rate and the other lapse rates. So here what you see is environmental lapse rate is this value, that is about 12 degrees C. So for every kilometer there is a 12 degrees C reduction, right? But at the same time, what is in the wet situation? It is 6 degrees C for every kilometer, right? And what is the situation of this parcel of air? It is again the 10 degrees C because it is dry adiabatic lapse rate. So where it is 30 in the same layer, it is 28 in the normal condition, that is environmental condition, right? Where it is 20, it is just 16. So what is the situation here? Can you see? Can you observe the situation? What is happening here? On the same layer, what is happening? The atmosphere condition, the normal environmental condition is actually lower, and this parcel of air is actually greater. So what will happen? What will be the tendency of this parcel? Remember, it is still greater than the normal. It means it will go further ahead, right? Then what you see, 4 degree, 14 degree, it will go further ahead. So this is the tendency of going ahead, and ahead. This is what the tendency is about, absolute instability. And why this happens? Because of the change of ELR, respective changes of temperature. If the environmental temperature in the layer is more, then what will happen? And if the environmental temperature in the layer is less, then what will happen? So these are the two cases. So remember what is here? This ELR is the greatest, right? So when it is the greatest, then absolute instability. So remember, when you see that environmental lapse rate or normal lapse rate is actually increasing, it means there is high convective situation happening. So that happens in extreme summers that we observe, right? Now, the next condition or the third condition is a conditional instability. Now, this is very interesting. Normally in ELR situation, that is normal environmental lapse rate, we understand how the situation operates. When ELR is greatest, it becomes very unstable. When ELR is smallest, it is a stable situation. So now let's look here. What is the environmental lapse rate? It is 9 degree. What is the dry adiabatic lapse rate? 10 degree. So this is greater, dry is greater, but wet is actually 6 degree. So this environmental lapse rate is falling in between this. Remember, 9 is the ELR and DALR is 10 and WALR is 6. So it is falling in between. So in this situation, what will happen after a particular altitude? Now this is interesting here, that after this 40 degree goes 30 degree goes 20 degree, this is a level where it reaches a dew point, Remember why? Because C, what is the change here? It is 22 degrees C, while at the same time it is 20 degrees C. So it means ELR is now greater here in this layer, and this is cooler. It reaches dew point. So when it reaches dew point, there is a change that is because of the latent heat. Remember, so latent heat is released of the condensation, cloud formation, rainfall happens, but after this latent heat is added, still the temperature goes up. Why? Because of this wet adiabatic lapse rate, it goes ahead and further ahead. So this is where it crosses the limit. So what we observe here is that till a particular point, which is a condensation level, till this point, what you observe? This is 20, right? And this is 22 degree, right? So what is this layer's property here? ELR is actually greater than DALR till this level. But once this latent heat is added, what happens? This particular latent heat does a change, and that is where in the next segment what happens? This is 13, 4 and 5, that is -5, but here the temperature has been added, so it is greater now. So this is where there is a change, it's shift. It means what you observe is due to this wet adiabatic lapse rate, there is again a change in this layer, and what you see, the warming is there in this parcel of air, and if it is warming, it will go ahead, right? So this is what is again an unstable condition or unstable condition, but till a particular extent it was stable. So what you observe is till a particular extent, that is till this particular height, when environmental condition is actually warmer and this is cooler, then it has a tendency to fall down. But after this, it has a tendency to pick up. This condition is actually driven by what? Latent heat. So latent heat is part of this wet adiabatic lapse rate, and that is what changes the equation. That is why it is called conditional instability. Now, the last part that we need to discuss is this mechanical instability. Now, remember what happens sometimes due to atmospheric anomalies, abnormal conditions, the normal lapse rate goes to high, to extreme, right? Almost like 35 degrees C. So suppose if normal lapse rate goes extremely high, what will happen? With each kilometer, there will be a major change in the temperature, major reduction in the temperature. So at upper atmosphere, there will be what happening? Automatically a cold situation created because of this high change in or high reduction. So upper atmosphere becomes extremely cold. So if it becomes extremely cold, what is the tendency? It becomes cold, it means it becomes dense, and it has a tendency to fall down very quickly as it becomes very cold quickly. So when it fall down very quickly thing happened, what is the situation here? It is a mechanical instability. It pushes the air down, and that is where this tornado is formed. That's where mechanical instability is important, right? So that is what we understand by the atmospheric stability and instability. So I hope you understood the stability part and instability part of the atmosphere in a clear manner. So stability is when the tendency is to actually subside down this air, and it will only depend upon what is the situation of environment and what is the situation of this parcel of air. If their temperatures are varying, in what ways they are varying, that is where the stability and instability we have to learn in case of normal lapse rate and dry and wet conditions of adiabatic lapse rate. And at last, we also need to learn about this fact that how do we measure this. So to measure this, there are certain indices which have been created. For example, if you see Bulk-Richardson number, lifted index, K index, convective available potential energy, that is called CAPE, and Scholter, then vertical totals. All these things, you just remember the names at least, don't go into the details, but these are important indices that are used to actually determine or measure the atmospheric instability. You can pause the video and see for yourself how this K index actually denotes the thunderstorm probability. So the value and associated thunderstorm probability is here. Then lifted index is something which is also very interesting. So when lifted index is positive, it means a stable atmosphere. If lifted index is negative, it means an unstable atmosphere. So these are important indices. So this is what you need to also remember along with the conditional situation of instability and stability depending upon the lapse rate and the adiabatic lapse rate of dry and wet condition. So remember this atmospheric stability and instability conditions. So now, when we have discussed the nuances and details of this atmospheric stability and instability, in the lectures to come, we are going to learn about the winds of different types, that is planetary winds, seasonal winds, local winds. So stay tuned, stay safe and keep watching.